Hello, everyone. Thank you for listening to this, and thanks a lot to the organizers for having me. I'm going to tell you about efforts to analyze the full probability density function, or PDF, of cosmic density fluctuations. And this is work that I've been doing with a lot of collaborators, some of which you see listed here. Now, first, a couple of words on what is the PDF of density fluctuations. On the left-hand side of this slide, you see a dark matter density map on the sky from the buzzard n-body simulations. And to create this map, we took the matter density field in buzzard and projected it along the line of sight between redshift of 0.2 and 0.5, and then averaged the resulting map on a smoothing scale of about 30 arc minutes. And in the right-hand side of this figure, of this slide, you see a cutout from this map in the shape of the year one footprint of dark energy survey data. Now, in real observations, we of course don't have direct access to the full matter density field. Instead, what we will see is galaxies. And on the next slide, I show you within the same simulation and also within the same redshift interval, maps of the matter density, the density field of galaxies. In this case, red magic galaxies. So this would be a sample of luminous red galaxies that's being used in the dark energy survey. And if I flip back and forth real quick between these two slides, and if you focus on the right-hand side of these slides, then you will see that these two fields, the matter density field and the galaxy density field, are indeed correlated. But there's also some noise, some stochasticity going on between the two. And now, what is the PDF of density fluctuations? So it's basically taking these two maps and measuring a histogram of them. Yeah? And this is exactly what I'm showing here. On the left-hand side, you see in the lower left corner, the x-axis is representing matter density fluctuations, again smoothed on these 30 arc minutes smoothing scales. And on the y-axis, you see galaxy density fluctuations. And for the orange dots, just for visualization purposes, I've just taken a random subset of pixels in these two maps that I showed you before and just enter them here in this two-dimensional plane. And the red lines that you see is the contours of the distribution of all the pixels in these maps if you were to put them on this plane. Now, what you can see is there is certainly a strong correlation between matter density and galaxy density fluctuations. But you can also see that galaxies aren't perfect traces of the matter density field, but they will be biased and stochastic, where biased means that the slope of this correlation is not going to be unity, and stochastic meaning that there is some scatter between matter density and galaxy density fluctuations. And now this distribution is what you would call the PDF. And the most common approach of analyzing large-scale structured data, which is two-point statistics, would actually compress this distribution quite strongly. So at any given smoothing scale, two-point statistics would really just extract three numbers from this PDF. It would extract the variance of matter density fluctuations, the variance of galaxy density fluctuations, and the covariance of the two. And what me and my collaborators are trying to do is to go beyond this strong compression and analyze the full shape of this distribution. And what you see in the red contours in this figure is a theoretical model prediction that is presented in this paper of me et al. 2018 for exactly this distribution. Now, what I want to do on the next couple of slides is I want to tell you a bit about the details of this model prediction. And I want to show you that this is indeed not a complete black box, and what's going on in this model can be made transparent and easy to understand. And to do that, I'm going to compare quantities of two-point statistics to corresponding quantities or analogous quantities on the PDF side of things. And yeah, let's start with the power spectrum. As you all know, the power spectrum on the two-point side of things is defined as essentially the variance of Fourier modes of the density field. So this is what I'm indicating here. And now the analogous quantity on the PDF side would be what is called the cumulant generating function. And this cumulant generating function is a power series in terms of some variable lambda. And this lambda you can really think of it's the equivalent of the wave vector k in the two-point function case. And the power series coefficients here will be given by the so-called nth order cumulants of the density field. So given a certain smoothing scale R, these cumulants are the so-called connected parts of the central moments of the density field. So this would be the parts of the central moments that would identically vanish if you had a perfectly Gaussian random field. Yep. Now, moving on. For two-point statistics, there's also an alternative observable, which is the real space two-point correlation function. And the real space two-point correlation function and the power spectrum, which is the Fourier space two-point correlation function, they will be related by a Fourier transform. And this is what I'm writing here. And now the situation is the following. Cosmological theory will typically give you a prediction for the power spectrum. So primarily it will predict the shape of the power spectrum. But if you measure the two-point correlation function, the real space two-point correlation function, instead, then what you will have to do is you will have to take your theory prediction for the power spectrum and Fourier transform it to obtain a prediction for the real space two-point function. Now, on the PDF side, something very similar happens. Your actual observable is usually not going to be the cumulant generating function, but instead it's going to be the PDF, this histogram that we just talked about. But theoretical calculations will primarily tell you about the CGF, so the cumulant generating function. And the nice thing is that PDF and CGF are related, this time not by a Fourier transform, but by a Laplace transform. So if you want to have a theoretical prediction for the PDF, just take your prediction for the CGF and apply an inverse Laplace transform to it, and you're going to have a prediction for the PDF. Now, one important thing that you need to know is, of course, how do your quantities evolve over time? And on the two-point function side of things, for the power spectrum, at leading order in perturbation theory, we know that the growth is linear. So the power spectrum will just grow proportional to the square of some growth factor, d of t, which doesn't depend on scale, but only on time. Now, this is where the PDF side becomes a little bit more complicated. And in this paper of me et al. 2020, we use a path integral formalism to derive that a leading order approximation for the cumulant generating function, given general non-Gaussian initial conditions of the density field, will be given as the minimum of this two-dimensional function that I'm writing here in the second equation on the left-hand side. And now this may look rather complicated, but you can attempt to think of this in two simple steps, really. First of all, note that here on the right-hand side of this equation, what I'm writing is the cumulant generating function of the initial density field. And for Gaussian initial conditions, this would, for example, just be a quadratic function of some variable j. Now, if you want to calculate from this the late time cumulant generating function, then in a step one, what you're going to do is you're going to take this initial cumulant generating function, which is again a function of some variable j, and you're going to apply a Legendre transform to it, and you're going to obtain some function of a new variable delta. And then in a second step, you're going to apply an inverse Laplace transform, but this time not with respect to the variable delta, but with respect to a transformed variable f of delta, where the function f is essentially given by spherical collapse. And yeah, like I said, we used a path integral formalism to derive this formula. There's also other ways to obtain this, for example, within large deviation statistics. And I must say that at this point, I can't really do justice to the literature, unfortunately. But at the very least, I want to mention these papers that you see down here. So this is a set of papers which subsequently develop more and more of this PDF theory that I just told you about. Now, one last important step in our theory calculations is the following. Unless you have direct access to the three-dimensional density field, you're typically going to struggle with line of sight projections. So for example, in a photometric survey like the dark energy survey, you'll typically look at line of sight projected density fields. And on the two-point function side of things, fortunately, there is something called the Limber approximation, meaning that the two-dimensional power spectrum, P of L, can be calculated as a line of sight integral of the three-dimensional power spectrum, where here the integration variable W would be co-moving distance, and Q of W would be the projection kernel by which you have projected the density field. And something very similar happens on the PDF side of things. The cumulant generating function of a projected density field on the sky can be written as a line of sight integral of cumulant generating functions of the three-dimensional density field, where this time the filter of your density field will be a cylindrical filter. And this is, by the way, also why it is often more easy to work with the CGF in the first place as opposed to directly obtaining models for the PDF in 3D, because in photometric observations, you're going to have to deal with projected versions anyway, and then you will need to make use of this Limber type of approximation. And yeah, this concludes what I wanted to say about the theory. Now you might ask yourselves, how well does this work compared to realistic density fields? And this is why I'm showing you here comparisons of this type of modeling to n-body simulations. First of all, here in the upper left corner, you see a figure from this paper, Mi et al. 2020, where we compare our model to measurements of the PDF in the Quixote n-body simulations. So in orange, you see the measurement of a measurement of the PDF in Quixote, where we have smoothed the density field on a 15 megaparsec scale. And in blue, you see our theoretical prediction, and you see that matches quite well. And now on the lower right corner, you see that this kind of theory also allows you to model quite subtle effects. So what we're showing here is the dots in this figure denote measurements of PDFs in the so-called Oriana simulations. And what we're showing is the difference between PDFs from Gaussian initial conditions and PDFs from different types of non-Gaussian initial conditions. And in the solid lines, you see, again, these theory predictions based on exactly that equation that I showed you 2 slides ago. And you see, we can even model these kind of complicated effects quite nicely. And so I'm going to repeat this toward the end of the talk again, but let me just say this now already. All of these calculations you can actually do yourself, because we put together this publicly available Cosmomentum tool. So if you just go to this GitHub repository, you will find C++ code and Jupyter notebooks to run exactly these kind of theory calculations. Now moving on, and here I'm showing you again this figure from the very beginning of the talk. Note again that here the blue line is also a theoretical prediction. And this shows you that in this type of modeling also works in projected data, because remember, this was actually a line of sight projected version of the matter density field. And yeah, also in that situation, we can at least describe n-body simulations well. Now, since this is a workshop on observational cosmology, you might ask yourselves, does this work on real data? And so to that, my answer would be, partly we have done this already in real data. In DSU1, we put out an analysis of so-called density split statistics. And this technique basically uses gravitational lensing to scan through the galaxy density PDF. So we're taking the galaxy density PDF, we cut it into stripes, and within each stripe, we use gravitational lensing to tell us what the matter density in that stripe is. And this way we can quantile by quantile connect the galaxy density PDF to the underlying matter density PDF. And this analysis was based exactly on the type of modeling that I just explained before. And if you're interested in more details of this, please consult our papers. This would be me et al. 2018 and Grun et al. 2018. In this talk, unfortunately, I won't go into any more detail about this. Instead, I want to look at the future and at next steps that we might attempt to take. And one thing that we're currently attempting is to push this approximate treatment of density split statistics to a more direct analysis of the PDF of matter density fluctuations. So we really want to analyze the full shape of the PDF this time. And the kind of data vector that we have in mind is depicted here on the right-hand side. Here you see, of course, we don't have direct access to the matter density field. Instead, what we'll have to do to use is gravitational lensing. And here you see on the y-axis the convergence field of gravitational lensing of the cosmic microwave background. So this would be our tracer of matter density. And yeah, you can just think of this really as a line of sight projection of the total matter density field in the universe. And on the x-axis, we have counts of a sample of galaxies, in this case, aiming at a luminous red galaxy sample. And so in the following slides, what I will assume is that we have such an LRG sample within redshifts of 0.6 and 0.9, that we have a CMB convergence map with noise properties similar to that of the South Pole Telescope survey. We're going to apply a 20 arc-minute smoothing to both of these data sets. And we're going to assume that we have 5,000 square degrees on the sky. So part of these assumptions are slightly futuristic, especially SPT doesn't yet cover the full 5,000 square degrees of DES. But yeah, in the future, we will for sure have, in the near future, we'll have data sets very close to what I'm describing here. And now the data vector that we're going to look at is going to be this PDF that you see here, but pixelized on a grid of 20 by 20. And then we're going to use just the pixels in the innermost part of the PDF, namely those pixels that together give about 90% of the total probability. And on the next slides, I want to show you how this type of PDF would react to different model parameters. So in all of the figures that I'm going to show you now, the black contours that you see here are still the contours of this original PDF that you saw before. And the color maps and the orange contours will represent a derivative of this PDF with respect to different parameters. And dashed contours, dashed orange contours meaning negative derivative. And we start with sigma 8, so with the overall amplitude of fluctuations. And clearly you can see that if you increase the overall amplitude, then what's going to happen to the PDF is the peak of the PDF is going to dip down and the flanks of the PDF are going to go up. And this is probably naturally what you would expect when increasing the width of the PDF. But there's also another effect going on here, and this you can see from the asymmetry of the orange contours. So you can see that the derivative of the PDF is much higher here in this low density regime than it is in this high density regime. And this is exactly because an increase in sigma 8 doesn't just increase your variance of fluctuations, it also increases your skewness of fluctuations. And at this point, remember that 2-point statistics would really just extract the 3 second moments of this distribution. So the variance of galaxy density fluctuations, of matter density fluctuations, and their covariance. So with 2-point statistics, you actually wouldn't capture this kind of increase in skewness. And this is exactly where potential additional information of a full shape PDF analysis is coming from. Now, Moving on to galaxy bias. So this time showing you the derivative of the PDF with respect to linear galaxy bias. And here it's also quite clear what's actually going on, right? If you increase galaxy bias, you only increase the amplitude of galaxy density fluctuations, leaving matter density fluctuations untouched. So clearly you're going to get this kind of horizontal pattern in the derivative, as you see here. And finally, let's also look at stochastic bias. So here I'm showing the derivative of the PDF with respect to a stochastic correlation coefficient between galaxy density fluctuations and matter density fluctuations. And here clearly you can see if you increase this correlation, then you're going to change the diagonal structure of the PDF. So you're going to increase the PDF on its diagonal. And this is also what you see here. And yeah, this is exactly the nice thing about analyzing the full shape of the PDF, because all these different parameters which give very similarly looking signatures in 2-point statistics, they give very different and rich patterns in the full plane of galaxy density and matter density fluctuations. So you can hope that with such an analysis, you can recover much more cosmological information from the large scale structure. And so what we wanted to see is whether the statement that I just made, indeed, to what extent this statement that I just made is actually true. And to do so, we attempted to make to put together a Fisher analysis and trying to find out how well can we measure certain cosmological model parameters. And of course, to do that, what you need, first of all, is a covariance matrix. And at this point, I want to highlight this work by Annick Halder, who is a PhD student in Munich and who is doing a lot of good work on this project. And he has put together simulations based on this Flask tool, which gives you log normal realizations of cosmic density fields. And yeah, we came up with certain ways of combining a set of log normal fields in order to really capture the non-Gaussian correlation structure of the cosmic galaxy density and matter density fields. And as you can see here on the right-hand side, indeed, these more complicated log normal simulations agree quite well with our theory calculation in terms of the PDF. So we're optimistic that it gives us a realistic covariance matrix. And then, like I said, what we're going to do is we pixelize this in a grid, and then we're going to put all the pixels in a row. And this is basically our data vector. So the one that you see here in the lower right corner. And so based on this data vector, we can now go forward and do our analysis. And yeah, what you see here is Fisher contours that we get for exactly that data vector that I described and this covariance matrix. In blue, you see this PDF analysis. And yeah, you see we can constrain all these different parameters: matter density in the universe, amplitude of fluctuations, linear bias, stochastic bias. And what you also see in green is a forecast using a covariance matrix for the most sophisticated 2-point function analysis that is currently around. This would be the upcoming year 3 analysis of 2-point statistics in the dark energy survey. And what I want to highlight here is that, remember that for the PDF analysis here, we are really just using one angular scale and one redshift bin, plus the CMB convergence map, of course. Whereas in this 2-point function analysis of DES, we're using 18 different angular scales and 9 different redshift bins. So it's way more sophisticated analysis, but still you see the PDF analysis manages to be quite competitive. And to some extent, you see, you can even hope to break degeneracies that would be there in the 2-point function analysis. Now, on the next page, on the next slide, I'm going to show you something that is admittedly a bit of a stretch, because here we also added an additional parameter, which is the amplitude of the initial 3-point function of the density field, FNL. And well, obviously, you see here that our constraints on FNL are not competitive at all. But what I want to tell you with this slide is that remember that fixing 2-point functions onto one angular scale, you would only be able to obtain 3 numbers. But an analysis of the full shape of the PDF is already constraining 5 different properties of the universe here in this figure, yeah? And so this really shows you that there is lots more information in the full shape than what's just in the second order moments of the distribution of density fluctuations. And this is exactly the type of figure that makes us really hopeful for the future. And just noting one more thing here, one reason why we are actually doing so badly with FNL is just because our projection kernel is so wide. So we're really projecting the density field from 0.6 to 0.9. And in Me et al. 2020, we found that you need to go beyond smoothing scales of 30 megaparsecs in order to get competitive with FNL. But this actually means that you could also be hopeful that with spectroscopic data, you could be much better on that front. Okay, so that is the state of affair. And this brings me to conclusions. Yeah, I was trying to show you that we can indeed open up this complete plane of density perturbations, of galaxy and matter density perturbations for large-scale structure studies. And even in a simplified analysis setup and with a rather complicated bias model, you can perform a complete and competitive lambda CDM analysis. And you even have the potential to break the degeneracies that are there in more traditional analyses. And there is much more, actually. I haven't even told you about this paper, for example, that I'm mentioning here, which is Cora Uleman, me, and others, where we investigated how to constrain neutrino physics with the full shape of the density PDF. And yeah, I want to close with just pointing you again to this Cosmomentum tool package. So yeah, we have set up this GitHub repository. And if you go there, you will find tutorial notebooks which show you how to compute 3-dimensional PDFs and cumulative generating functions, PDFs of the lensing convergence field, and 2-dimensional and 3-dimensional halo counts and cells PDFs. So if you're interested in that, please check out the code and yeah, let us know any comments or any questions that you might have. And that's it. Thanks a lot.